We are now into Unit 7, and Unit 7 is all about chemical reactions, which we are in a chemistry course, and now we are finally talking about chemical reactions. We had to do a whole bunch of foundational work, and we got into bonding where we learned about ionic compounds and covalent compounds. Now we can take those different compounds and make them react together, which means those different elements in those different bond types can rearrange and form new substances. Our first lesson is just going to be a general introduction to chemical reactions, signs of chemical reactions, what the different symbols in a chemical reaction equation means, and what the basic 5 types of chemical reactions are for an intro to chemistry course. Eventually, we will use this knowledge and be able to, on our own, actually be able to write our own chemical reactions and predict the products if I give you reactants, which is super cool. All right, so let's get started on our intro to chemical reactions. Well, what is a chemical reaction? Oh my goodness. A chemical reaction is a process where one or more substances called reactants are transformed into different substances called products. This transformation involves a rearrangement of atoms in some sort. Atoms are rearranged by breaking old chemical bonds in the reactants and forming new ones to create new products with different properties. So here's a reaction equation of taking hydrogen and oxygen and turning those into water. And when I say turning into, I'm not saying I have created or destroyed matter. I am not saying any one of these hydrogen atoms have disappeared or oxygen atoms have reappeared from nowhere. I am just saying that the bonds within these individual reactant molecules are broken in some way, and then they come together and form new compounds. If you'll notice in my reaction equation here, I have 2 overall H2 molecules, right? We know that hydrogen is one of my diatomic molecules, which means that if you were to have a sample of pure hydrogen, he will always come in 2s. But I have 2 of those H2 molecules. If you'll notice in my reaction equation, I have 1 oxygen molecule. Oxygen is also a diatomic. He comes in 2s when he is by himself and not in a compound with other atoms. And then they rearrange to make 2 water molecules. I can look on both sides of the reaction equation. I will see the same number of blue things as I see the number of red things. This is law of conservation of mass in action. Okay, so as I mentioned, we are breaking bonds on that reactant side, and we are forming new bonds when I create those products. The law of conservation of mass. Matter is neither created nor destroyed in a chemical reaction, only rearranged. So this means that the number of each kind of atom on each side of the reaction must be equal. And it also means that the masses of the reactants and the products on each side of the reaction also must be equal. So let's dive into that a little bit more. So the law of conservation of mass states kind of 2 things, that the number of things needs to be the same and the masses of things on both sides of the reaction needs to be the same. So let's say I'm doing this reaction here where I react methane with oxygen and turn it into carbon dioxide and water. If you'll notice, my black circles are carbons. I have 1 carbon on the reactant side. I also have 1 carbon on the product side. My white circles are my hydrogens. I have 4 here on my CH4 molecule on the reactant side, and I also have 4 here on the product side. And then finally, the red circles are my oxygens. I have 4 of those on the reactant side, and I have 4 of those on the product side. Now, in what condition they are, that's going to be different, meaning they are going to be coupled up with maybe different elements to make different substances, but the number is the same. I'm conserving mass in that way. I can also here give you some mass values. If I say I'm starting off with 4.5 grams of methane and I use up 1.5 grams of oxygen in this reaction, that means I have a total mass of 6 grams of reactants. That means on the product side, I also need to have a total mass of all of my products being 6 grams. That mass has to be conserved, which is why you see the combined mass of the carbon dioxide and water will get you that 6 grams. Okay, so the number of atoms and the masses on each side of this reaction must equal each other in order to conserve mass. All right, signs of a chemical reaction. There are some things that we can see or observations that we can observe. Things that we can observe that will let us know that maybe a chemical reaction has occurred here. Let's see what they are. This should be mostly a review. We know if I see light and fire probably something chemical reaction-y is happening, right? If there's a formation of an odor of some sort, if there's an unexpected temperature change, meaning something gets really hot or really cold suddenly, if there's an unexpected color change, if there's a formation of a solid precipitate. We have learned that a solid precipitate is a solid that is created, a solid ionic compound that is created by mixing together two aqueous solutions of ionic compounds. And then a formation of gas. If I see bubbles in the bottom of my beaker bubbling up, then I know that I've got a chemical reaction that has occurred. Okay, let's talk more about like the reaction equations. What are all these symbols? What are all these signs? What are these numbers we got going on here? Okay, so we write chemical reaction equations to represent which substances are used up. We call those reactants, and which substances are formed. What is a chemical equation? A chemical equation is a written expression or representation of a chemical reaction. And I know there's a lot of different like labels and stuff here. We're going to dive into those one-on-one here in the next few slides. But first I want to give us kind of like an example here. Let's say I mix aluminum and bromine together, and I see that I create aluminum bromide. So I can actually, with words, say these things. So I can have the names of the things that I'm trying to combine together. Aluminum. If you'll notice, I have an S in parentheses. Whenever you see an S or an L or even an AQ, that represents what state of matter that substance is in. So it says aluminum, and it means it's a solid form, which I can see here. And then I mix that with bromine, who is a liquid, and then I create this new substance called aluminum bromide, a solid. Okay, now I can take those words, y'all, we know nomenclature. You can actually turn these words into the formulas. And hopefully it's not too tricky for you to grab the symbol from aluminum on the periodic table and be like, bam, Al, okay? Probably not too tricky for bromine either, except, oh, notice after I write Br, I give him a 2. That's because he's one of my diatomics, and we know if a diatomic element is by himself, this sample of bromine here on the reactant side is, he will always come in 2s, which is why that subscript 2 gets assigned to him. And then finally, aluminum bromide. That's an ionic compound between the metal aluminum and the nonmetal bromine. I would identify what their charges are, their oxidation numbers from the periodic table, and I'm able to crisscross those down to realize that I will need 3 bromines, each with a -1 charge, to neutralize my 1 aluminum who has a +3 charge. So we have now used a formula, our knowledge on how to do nomenclature, to actually create this reaction equation. But I'm not done. In fact, let's go back here. As I look at this, according to the law of conservation of mass, I need to show my reaction equation showing the same number of items on both sides. Aluminum looks like it's good. It looks like I have 1 aluminum on the reactant side and 1 on the product side, but my bromines are where things get wild. I have 2 on the reactant side here, and 3. I cannot create a bromine atom out of nowhere, okay? I've got to do something called balancing, which means I'm gonna put some big numbers in the front of these formulas to make sure that law of conservation of mass is true for this equation. So if you'll notice, I've put a 2 in front of the aluminum, I put a 3 in front of bromine, and I put a 2 in front of aluminum bromide. So we'll get into a whole lesson on how I put these numbers and how I figure out what numbers goes in front of who, but the reason why I put those numbers is that it will give me 2 total aluminums on both sides of the reaction equation, and 3 times 2, 6 bromines there. 2 times 3, 6 bromines there. So I have conserved mass, which is super exciting. So we balance all chemical reactions in order to satisfy the law of conservation of mass. To do this, we add large numbers in the front of reactants and products so that equal numbers of each element on each side of the equation are represented. These big numbers are called the coefficients. So we're seeing lots of numbers in here. I'm kind of getting a little nervous. Well, these numbers that we see, we can classify them into one of 2 categories, either coefficients, which are the big numbers in front, or subscripts, which we know come from the actual formula that I have to write down, right? So the subscripts are the small numbers within a formula. Coefficients are the big numbers on the top. This is very exciting. I have a rooster that is crowing like crazy outside, so I hope that that is audible on this video for everybody to enjoy as well. So now I have some symbols. So here are a list of some common symbols that you will maybe see in a chemical reaction equation. The most obvious one for us to address first is this arrow. That arrow is a yield sign. It lets me know the direction that the reaction is progressing, meaning it will start with reactants, and then that arrow points you towards the products that it is producing, right? Sometimes it won't be a single-headed arrow. Sometimes it will be a double-headed arrow. And that just means that that reaction has the ability to be reversed, which means not only can I take my reactants and turn them into products, I can take my products and maybe run them back into the reactant side as well. Occasionally, reactions will need to be heated in order for the reaction to occur. So we'll have this little triangle delta signal that's written above the arrow to let us know that heat is required for that chemical reaction to occur. We've talked about these state symbols, solid, liquids, gases. Aqueous means a substance is dissolved in water. So if I see those written after reactants or products in the chemical reaction, I'm just letting you know what state of matter it is in. And then occasionally we will have a reaction that will not occur, to which in case I would write on the product side an NR, letting you know that there's no way that that reaction could occur. And we'll talk about some of the reaction types where we will be applying the NRs for those. All right, types of chemical reactions. So, okay, y'all, there are thousands of different types of chemical reactions. Like, oh my gosh, so many. But for this intro chemistry course, we will be classifying our types of reactions into 5 main categories. You will be responsible for knowing these 5 main categories in terms of identifying them and predicting the products that will be created from a reaction from one of these 5 types, which is a super powerful skill. Okay, so my 5 types of chemical reactions. Synthesis means bringing things together. So if you'll notice, I have A plus B. So I have 2 reactants. They come together and I have one product that is now a combination of A and B. Single A and Bs to make a couple A and B. Decomposition is the exact reverse of synthesis, where I take a compound and then I break it up into 2 different products. A single replacement is a little bit different here. On the reactant side, I have a single element and I have a compound between 2 different elements. But then on the product side, I have something a little bit different. I've got a different compound and a different single element. So we call it a single replacement reaction or a single displacement reaction because this single guy actually kicks somebody out of the compound and he will now form the compound with the remaining element. A double replacement, I got a little bit more going on here. I got 2 compounds and y'all, they're going to switch partners in some way to have that double replacement happen. And then finally, my combustion reaction, y'all are like, what is going on here with these X's and Y's? A combustion reaction is any reaction where I have a hydrocarbon compound, which means something that has hydrogen and carbon, and I burn it in the presence of oxygen. The cool thing about combustion is that you will always get these 2 products, carbon dioxide and water. Now, if you'll notice in the 4 reaction types above combustion, I have like A, B, C, and D. Those do not stand for a specific element. I can put any element from the periodic table in an A, B, C, or D classification. So it gives you a lot of opportunities or varieties of different types of synthesis, decomposition, single, and double replacement reactions. Combustion, I must see a hydrocarbon and oxygen as my reactants, and carbon dioxide and water as my products, okay? All right, so y'all are like, this is, oh my gosh, so intense. I agree, it is just like, I'm bored already. Y'all, I like to talk about my chemical reactions as if it was a tale of romance drama. Like synthesis, for example. Some couples are just meant to be. Here we have Travis Kelce and Taylor Swift. Guess what, you guys? They came together to make a couple trailer. If you'll notice on the previous slide, I wrote Travis Kelce in red and I wrote Taylor Swift in blue. Now they are a couple The red, Travis, comes first, and the blue, Taylor, comes second. If you'll remember in my class, I like to use my reds and blues to represent metals and non-metals. So this would totally be a case of a metal guy and a non-metal girl where they were single. Now they have joined as a relationship between the metal and the non-metal. That's true love, you guys. Okay, well, Travis and Taylor are not like chemistry stuff here. Okay, in chemistry terms, a synthesis reaction occurs when two, or sometimes even more, reactions combine to form one new product, okay? And here's my reds and blues again. So here's an example of A plus a nonmetal B creates a compound, an ionic compound if I have a red thing and a blue thing. And yes, remember the red metal is always written first. In real life terms, y'all, I could take magnesium, he's a metal, and I can make him react with oxygen, a nonmetal, and they will make an ionic compound, magnesium oxide. Now, we did this demo in class, but if you were not in class, we will totally watch this fun video on the reaction of magnesium with oxygen to make magnesium oxide.
Well, some other metals are even more reactive than the iron that we saw, and one of these is magnesium. Magnesium is just a silvery metal. This is in the form of magnesium ribbon here. And this burns in air very easily and gives out a lot of energy, in the form of light and heat, but a brilliant white light. So you can see this here. Bring the lights down, please. So a brilliant white light as the magnesium reacts with the oxygen from the air. And if we have the lights back up for a moment, please, well, you can see the smoke that's being formed here. This is magnesium oxide that's formed during this chemical reaction as the magnesium combines with the oxygen from the air. And if we manage to trap all of this smoke and the ash that's left here, we would see that that would also be heavier than the metal itself, than the pure magnesium. This is as the magnesium combines with the oxygen. So the chemical equation for this is magnesium reacting with oxygen to form magnesium oxide, and again releasing a lot of energy in the form of heat and light.
All right, so I also saw some signs of chemical reactions from that. I saw a lot of light coming from that chemical reaction. But yes, you guys, when I have two single elements come together to make a compound, or two single people, my Travis and Taylor, come together to make a couple, that is a synthesis reaction. Another real life example, you guys, we know that iron rusts. Well, that's actually a chemical reaction. Here I've taken iron and it is actually reacting with the oxygen in the air and making a new compound called iron 3 oxide, okay? So single iron, single oxygen makes a couple between iron and oxygen. All right, so if I had synthesis, which is when a couple gets together, you guys, decomposition. Oh, sometimes if a little heat is added to even a perfect relationship, like Joe Jonas and Sophie Turner, a breakup happens. You guys, this is decomposition, okay? I had a couple between a metal Joe Jonas and a non-metal Sophie Turner. They have broken up. They are now single people. Yes, that's a decomposition reaction. Now, in chemistry term, it says decomposition reactions occur when one reactant, meaning a couple, will break down into two or sometimes more products. And in order to break down into sometimes more products, you would have to have a little bit more going on in the chemical equation than just a simple ionic compound made up of two elements. But that is also a possibility. If you see one thing on the reactant side and two or more on the product side, you have decomposed something. You have a decomposition reaction. And if you'll remember, I mentioned a little heat being added. A lot of these decomposition reactions have to happen with something to kind of kickstart it, like some heat or energy added. So this is an example of mercury oxide. Yes, I have metal, mercury, non-metal oxygen there, a couple there. So super happy until no, conflict and a breakup. So mercury is now by himself and oxygen is now single by himself. Okay, here's a real life example. You guys, I can decompose hydrogen peroxide into hydrogen gas and oxygen gas by adding manganese dioxide. You're like, why is that written above the arrow? If you see a symbol written above the arrow, that means it is a catalyst. It is not involved in the chemical reaction. It does not move around and break bonds and stuff. It just helps get a chemical reaction started. So I thought we could watch this real fun video of showing how manganese dioxide actually helps hydrogen peroxide decompose. So that reaction was pretty intense. And you know what? If you've ever gotten a bottle of hydrogen peroxide, you can get it from the grocery store, from the pharmacy. It comes in this brown container where you can't see the liquid on the outside. That's because hydrogen peroxide actually will decompose into the two gaseous products if it is exposed to light. So it's much less able to do that quite as quickly if you keep it hidden away from the light. But the manganese dioxide really helps speed up that decomposition for sure. Okay, so first of all, we talked about single people coming together and making happy couples. We've watched happy couples break apart. Let's get things a little bit more interesting. Let's talk about these single replacement reactions. So sometimes the temptation of a more attractive partner is too great to ignore. Okay, so let's look what we have here. You guys, we have Ariana Grande. She was married to this guy named Dalton Gomez. They were together. Look how happy they are, yes? And then she was in this movie where she played Glinda the Good Witch in Wicked, and there was somebody else in that movie with her, Ethan Slater. He played like a munchkin or something. But y'all, do you know what's gonna happen? Ethan Slater is going to take the place of Dalton, and we have a new couple, Ethan and Ariana. They are a new couple, and y'all, Dalton Gomez is now kicked out. He is single. So that sounds real harsh, but in a single replacement reaction, yes, somebody is going to kick out somebody in a chemical compound. Now, the determining factor of if somebody gets kicked out or not is the person in the couple will always be the more attractive person. Now, say what you will about the attractiveness of Ethan Slater. Ariana found him more attractive, apparently, than Dalton, which is why she wanted to be in a couple with him. Okay, so the more attractive person will take the other's place in the couple. That is a single replacement reaction. All right, in chemistry terms, single replacement reactions occur when one element replaces another in a compound. Okay, so here I have a cool little example here. We know hydrogen. I know he is a non-metal, but sometimes he's like, I love to be a metal, please. So we have hydrogen, and he is looking at the couple between copper and oxygen, and he is like, I would like to be with oxygen. But oxygen has to say, okay, well, are you more attractive than the copper that I am currently with? And apparently he is, because guess what? A hydrogen kicks out copper. Copper is so sad. He is not attractive enough. He does not get to be with oxygen anymore. And now I have a new couple being formed between hydrogen and oxygen. Y'all are like, who do we know in chemistry is more attractive? These are elements of the periodic table. Yes, but we have something called the activity series. And that is actually on the back of our reference chart. It's a ranking of the who's hot and who's not of the elements of the periodic table. So if you're using the activity series, you're going to determine if the element that's trying to replace the other is more, it's not attractive, it's more active. But higher up on the chart is the more active or the more attractive element. Very exciting. Okay, so that's wackadoo. So that's single replacement reactions, you guys. There's a really good real life example of these single replacement reactions. I have aluminum he's more attractive than copper. And I know this because if I mix aluminum, like aluminum foil, with a solution of copper 2 chloride, I will see aluminum kick out the copper. And I will know that aluminum is kicking out the copper because you will see the formation of that brownish copper on the top of the foil. So you will be making aluminum chloride now by kicking out the copper because aluminum is more active or more attractive than copper on the activity series. So let's watch a video demonstrating this.
Hey, welcome back to Ramsey Land. Today I want to show you the single displacement reaction between aluminum and copper chloride. Check this out.
All I'm using in this investigation is aluminum foil, a beaker, a graduated cylinder with distilled water, copper chloride, you can see what it looks like, and a concentrated solution of copper chloride that I made with distilled water. Begin by tearing off a piece of your aluminum foil and wadding it up so that you can fit it down the neck of your graduated cylinder. Next, cut a smaller square of aluminum foil to put over your beaker. Place the aluminum foil over the beaker so there's a small indentation where it can hold just a little bit of your solution of copper chloride. Now you're ready to pour a little bit of your concentrated solution of copper chloride over the aluminum foil to observe the reaction. Here we go. Now at first, nothing's going to happen because there's an oxide layer covering the aluminum foil. But pretty quickly you'll start to see bubbles, and that's when it starts to break through that oxide layer, and you'll see that there's copper that appears on the aluminum foil. So here you can clearly see copper on the aluminum foil, and that's because aluminum is so much higher on the activity series that in this single displacement reaction, copper chloride trades places with the aluminum, and you get down here in the bottom, you get, instead of copper chloride, you get aluminum chloride, and it changes color a little bit, and up here you can actually see the copper. That's the brown residue that you actually see on the aluminum there. The next way you can demonstrate the same reaction is by taking your longer piece of aluminum foil and simply lowering it into your graduated cylinder of copper chloride. And I'm just gonna make it a little bit smaller so it fits. I'm gonna put like halfway in so you can see the difference between both halves. You can see it's starting to bubble. This is an exothermic reaction. You can definitely feel quite a bit of heat coming off of it. And there's the copper. You can see those brown pieces of copper there falling down in the solution. Isn't that amazing? Look at that reaction. And your copper chloride is turning into aluminum chloride because aluminum is higher on the activity series than copper. Just look at all of that.
So that's a great example of a single replacement reaction. We see that copper is not quite as active as aluminum to where he does get replaced. Okay, so here's a question. It's like, well, what if the single element is not higher up on the activity series? What if that single element trying to come in is not quite as pretty or attractive as the element that is currently in the compound? So here's an example of a nonmetal attempting to try to displace the other nonmetal in a compound. The only thing is that poor iodine, he is not as active or attractive as the chlorine is. So if you want to think about it this way, magnesium is like, I've already have the more attractive partner. No, thank you, I do not want to be in a relationship with you, which is really harsh. But then that's when I would write this NR, the no reaction. One thing I do want y'all to know or notice about these single replacement reactions is my colors are always going to make sense. No matter what couple I have or what compound I have, you will always see a red and a blue. That means all couples being formed from this swapping out will always result in a metal and a non-metal. Same thing, you're also going to notice that the metal is always written first, okay? So you cannot do a single replacement reaction where the result of that is a new compound between two metals. Oh, no, no, no. You also cannot do a single replacement reaction to where the result is two nonmetals. It always must be an ionic compound with a metal and a nonmetal. Okay. Now let's talk about double replacement reaction. So these are not celebrities or anything. These are made up people. I got Jeff and Sally, and I got Bob and Julie. They are coupled up. They are happy, or so we seem. And then what if they swap partners to where I do not have Jeff and Sally or Bob and Julie? I got Bob and Sally, and now Jeff is with Julie. It's like that show that was on TV for a hot while there called Wife Swap, where you had two married couples swap partners just to see what it would be like living with someone else. So this is a double replacement reaction, you guys. Double replacement reactions occur when the elements in two compounds switch places, okay? So A and B is a couple between a guy metal and a girl nonmetal. C and D is a couple between a different guy metal and a girl nonmetal. And they are swapping partners, but what I want you to notice, the way that they swap partners is I still must have a metal and a nonmetal. A metal and a nonmetal. I will not do a swappity swap partners where you have two nonmetals and two metals, okay? You always must have an ionic compound, okay? So here's an example of iron sulfide. Yes, iron 2 sulfide, and he's reacting with hydrochloric acid. The iron says, I do not want my nonmetal sulfur, I want the nonmetal chlorine. So he becomes a new couple with iron 2 chloride. Similarly, hydrogen's like, I don't want my nonmetal chlorine. I would like this other nonmetal, sulfur. So he forms a couple with sulfur, meaning we have hydrosulfuric acid from that double replacement reaction. Now, here's the cool thing about double replacement reactions. They're super fun. A lot of them are precipitation reactions. We said the formation of a precipitate is a sign of a chemical reaction, and we said that the formation of precipitate happens when you mix two aqueous solutions of ionic compounds. And yes, they will produce a solid insoluble product that is called a precipitate. And the cool thing is a lot of times these precipitates that you're forming make really, really bright, cool colors, which is super exciting. Now, I can figure out if an ionic compound is insoluble or it wants to form a solid, a precipitate, because there's a list of solubility rules ranking these ionic compounds in terms of their solubilities, which we will practice using when we have our lesson on double replacement reactions. I thought we could now watch a video of the formation of this lead 2 iodide, which is a really, really cool and striking yellow precipitate color. So there you can see the super striking yellow color, and that's not just a color change, y'all. That yellow thing is actually a solid precipitate that if we let it sit and settle, you will see it form as that solid lead 2 iodide at the bottom. Now I want us to look in this chemical reaction equation. I see the metals are always written first and the nonmetals are always written second. So when they do swap partners, you need to still retain that same organization of the ionic compound. Also, a lot of double replacement reactions are acid-base neutralization reactions. Now, we will have an entire unit on acids and bases, but this is a great intro because it is a type of double replacement reaction, and we're learning about that now. So it says a neutralization reaction is when an acid and a base combine to produce a salt, which is any ionic compound. You're like, wait, I thought a salt was NaCl. Yeah. Table salt for sure, but any ionic compound is also called a salt. So here I've got an acid, hydrochloric acid. Calcium hydroxide is a common base. We do not need to know our bases yet. We will have to wait to the acid and base unit to learn all that. But here I've got an acid and a base, and when they swap partners, I make a calcium chloride, which is a ionic compound, a salt, and I make HOH, which is water. So we call this a neutralization reaction is because I take an acidic component and a basic component, which have very different pHs. I mix them together and now they are neutralized, okay? Very exciting. Oh, this is a salt. How ionic. Our fifth and final type of reaction is a combustion reaction. Combustion reactions are not like couples, like switching places and, breaking up and coming together. Combustion reactions are my one type of reaction where I'm looking for specific things on the reactant side and the product side. Combustion reactions occur when a hydrocarbon, which is any compound containing hydrogen and carbon, burns in oxygen. Carbon dioxide and water will be your product. So I'm not going to get a lot of variation from this oxygen, carbon dioxide, and water. I must see those three things. The only differences between my combustion reactions is what that hydrocarbon looks like. So looking here, you guys, I have an example here. That's a C2H6 hydrocarbon. I see carbon, I see hydrogen. Boom. He can react with oxygen to make carbon dioxide and water. I also see CH4. Yeah, that's a hydrocarbon too. He reacts with oxygen to make carbon dioxide and water. When I burn wood, guess what? I'm doing a combustion reaction. With heat, I'm forcing that wood to react with oxygen. You make carbon dioxide and water. So a lot of these combustion reactions are stuff that burns, okay? So methane is natural gas. I can use natural gas to burn on my stovetop, you guys. Propane gas in my gas grills. I am burning that, yes. Butane is found in my lighters. I am burning that. So all of these are hydrocarbons. So we use hydrocarbons to burn things for combustion. Okay, our real life example, our classic thing that we've been doing since the first day of school, our whoosh bottle. This is a combustion reaction. I use 90% isopropyl alcohol. Well, y'all, this is isopropyl alcohol. It's got some C's and H's. Hello, hydrocarbon. By me dropping a match in there, I'm forcing it to react with the oxygen, and that whoosh sound is a drastic release of carbon dioxide and water vapor. So I do it with isopropyl alcohol. I thought it'd be fun to see if this reaction actually works with maybe different hydrocarbons like methanol or maybe ethanol.
It's still burning. And let's get our cloth again. It's still burning.
So there are some slight differences in the kind of vigorousness of a combustion reaction depending on what that hydrocarbon is, which is super cool and super exciting. But all of these are combustion reactions. Okay, here's another real fun real life example. One of my favorite science experiments to do is to explode a gummy bear. And the explosion of a gummy bear is actually two different reactions happening here. First, what we actually do is a decomposition of potassium chlorate. I heat potassium chlorate until it turns into a liquid form, making potassium chloride, and oh, I've created some oxygen here. Then when I drop a gummy bear, which is made of sugar, it will react with that oxygen and it will create a lot of carbon dioxide in water. So let's see that in action. So that's amazing. I don't know if that gummy bear really deserved to die that pretty intense death, but it's always, just a great demonstration of not only a combustion reaction, but also a decomposition reaction to create that oxygen to be able to react with that glucose, the sugar in the gummy bear, to create the carbon dioxide and water. And guys, inside of our cells, they do this combustion reaction all the time. That's how we get energy. That's how our cells make that ATP in our mitochondria. We break down that glucose, and y'all, this is why we breathe in oxygen, because we need that as another reactant, right? And that's also why we breathe out carbon dioxide and water being the products of the reactions that go on inside of our cells for us to get energy from the food that we eat, which is amazing. Okay, but here's my summary, you guys. When I am trying to classify my reactions as one of these 5 types, I'm just looking at seeing what I have on the reactant side and what I have on the product side in terms of single people or couples, okay? If I see 2 single people on the reactant side, well, they are gonna make a synthesis reaction to make 1 couple. That will be a synthesis reaction. If I see just 1 couple, the only thing that person can do, or that couple can do, is break up into my two singles for a decomposition reaction. If on my reactant side I see a single element and a couple, that's where I'll be doing the switching partners to create a new single element in a new couple. And then if I see two couples, the things that they will be doing is that they will be swapping partners in a double replacement reaction to create two new and different couples. Okay, so on these first four, I'm just looking at single people and couples, and I can see what type of reaction is going to happen, even just looking at the stuff that I have on the reactant side. Now, my combustion reacting, I'm looking for specific things. If I see a hydrocarbon and an oxygen, that will be a combustion reaction, and I know the products that I will always create are carbon dioxide and water. Okay, so that was our intro to chemical reactions. We learned it's all about conserving mass, right? We learned that that's why we balance chemical reactions by putting the big coefficients in front. We reviewed the signs of a chemical reaction, and now we've classified our chemical reactions into one of these 5 main types. Next time I see you guys, we're going to really dive into balancing and practicing balancing chemical equations.